If I could have your attention, please. Good evening, ladies and gentlemen. My name is Frank Derbyshire. I'm the director of the University of Kentucky Center for Applied Energy Research. I'd like to welcome you all to this unique occasion. In fact, I'm not quite sure which way to turn here. I'm told that this auditorium has never been filled so much before. Well, I don't intend to drag out the proceedings. I would like to first of all start by inviting the University President, Dr. Charles Wethington, to give some welcoming remarks. Dr. Wethington.
Thank you, Frank, and ladies and gentlemen, thank you for being so patient. It's a rare treat to have a problem such as we had tonight to experience an overflow crowd, and I really do appreciate the fine work of the staff to get some of the latecomers here on the stage so that we could get seats for most of those of you who wanted to hear Dr. Teller tonight. With our speaker today, we all have the unique opportunity of learning a little bit of both history and the lessons history teaches us. First of all, let me say how proud we are to be able to host a man of Dr. Teller's stature and reputation, to host him here at the University of Kentucky. This event is one of the truly special occasions we treasure each year in bringing to the UK campus persons who have had a significant impact in shaping national policy or history, in this case, international history. My congratulations to Frank Derbyshire of the Center for Applied Energy Research for the foresight he has shown in bringing someone of Dr. Teller's stature to the university. His goal of annually bringing to the university a scientist of international stature is a goal we endorse, encourage, and applaud. Through the efforts of the Center, the College of Engineering, the Kentucky Geological Survey, and others on campus, I believe that the University of Kentucky is making a difference in the quality of energy research that is being done in the U.S. today. I welcome each of you this evening. We're in for a rare treat. It's my pleasure to be a part of this ceremony this evening.
Thank you, Dr. Wethington. I'd now like to ask the Vice President for Research and Graduate Studies, Dr. Fitzgerald Bramwell, to make some opening remarks.
Good evening. It is indeed a pleasure to see such an overflow crowd for something besides basketball. In particular, it's important to realize that this research effort goes towards one of the key elements for our university, which is the creation and discovery of new knowledge through research. And toward that end, I'd like to particularly thank the Department of Physics, Department of Chemistry, School of Engineering, School of Medicine, for their efforts and their financial support of this particular gala event. Toward that end, as you know, CAER is the heart or the lifeblood of this event, and it is indeed in its 20th anniversary here. This is the third of a series, but the second speaker, and my gosh, it's a pretty tough road to follow. They have Dr. Teller, who indeed is a father of a number of things which indeed are of critical importance to our growth as a society. And so toward that end, I hope that you will all, particularly if you're of the generation of my 4 children, pay a special attention, because this opportunity may not come again. So toward that end, I welcome you all here, and thank you for your turnout.
My last duty is to introduce Dr. Bertrand Davis, who's an Associate Director at the Center of Applied Energy Research, and he is the person who was so instrumental in bringing Dr. Teller here, and he will make the introductory remarks.
Well, it's a pleasure to see such a large crowd to come here. A physicist, he dates back to what most of you have heard as the beginning of quantum mechanics and the application to atomic spectra. As an aside, he worked on weapons And that is what he will describe tonight, the history of nuclear weapons. And in this instance, the speaker has a longer history than nuclear weapons. So it's a pleasure to introduce Dr. Edward Teller.
Could I have a little less light so I can see the audience? They don't want to see me, they want to hear me. And I want to see how many of you go to sleep. I will try to talk briefly about a very many-sided subject. I obviously will be quite incomplete. I hope that when I stop, and I hope I will, I hope to have plenty of questions. The questions need not be polite. The questions need be short. And I will promise you to answer every question, to give you an answer whether I have one or not. So believe everything what I give in my talk, and believe my answers at your own risk. I want to go back to a time when not many of you were alive. 1943. I spent a year, a very wonderful, interesting year, in Copenhagen, Institute of Niels Bohr. Came back to where I was supposed to be in London, and one of my Hungarian friends, whom I have known, was a little more than 10 years my senior. I have known when I was a high school student. I hope you have heard about him. His name was Leo Szilard, S-Z-I-L-A-R-D. And he told me that one should use, put to practical use, nuclear energy. And he told me that he saw the great man who first measured nuclear energy, Lord Rutherford, and he would not hear about it. And very shortly afterwards, I remember a meeting of the highest assembly of British physicists. I heard Rutherford talk. It was incredible. More than half his time he spent on this stupid idea. Really, people want to use nuclear energy. Well, that's pure science. It never can be used. Well, he said that at least a dozen times, and in great detail, so I could, if I could reproduce his talk, say nothing more to you here. Szilard actually had some concrete proposals that did not work out. 2 years later, 1945, I found myself in the United States at the George Washington University, Washington, D.C., teaching physics and doing physics research very happily. And we had an annual conference. And at that annual conference, the great physicist Niels Bohr arrived and gave us the story that uranium splits. Now that is a remarkable story in itself. You know that atomic nuclei are composed of two kinds of particles. They are quite similar, except one is charged, one is not, the proton and the neutron. And the story we heard, the preliminary to the story is that when the neutron was discovered, a young, forward-looking physicist, a very wonderful man, in Rome, Enrico Fermi, used neutrons to bombard every element in the periodic table. The neutrons got attached to the nuclei. The nuclei, many of them became radioactive. He discovered scores of radioactivities. But if he bombarded one particle, one kind of particle, sodium or whatever, he got just 1 or 2 radioactivities. But when he bombarded uranium, he got 3 dozen. He interpreted uranium, is the heaviest natural element. And Fermi interpreted his results as his having produced elements heavier than uranium. And for that, he got the Nobel Prize. Now, the funny part of the story is that Enrico Fermi, in his long career, made only one mistake, and that was to believe that he made transuranic elements. And for that one mistake, he got the Nobel Prize. A few years later, 2 German physicists, Hahn and Strassmann, in the Kaiser Wilhelm Institute in Berlin, discovered the truth. Uranium is so heavily charged that due to the repulsion of the electric forces, it is ready to split. Not quite ready. But you add a little energy and it splits. That is fission. We heard about it. I could tell you lots more. The point is that when the conference was over, all the guests were gone home. My wife and I relaxed. Telephone, Szilard. When I can see you. Came down in a few hours. He wanted to know about whatever we heard about fission. Because in that process, while the uranium splits, some neutrons might get loose. And then, if from one splitting more than one neutron gets loose, that can cause more than one splitting, and you get more and more, and after this thing multiplying itself 50 times, the whole material goes up. That is the way how to release nuclear energy. And he was right. It was a sheer guess. He told me about it coming down for a visit and seeing a few people on that occasion. But not many weeks later, he called me away when I was just trying to, not very successfully, play with a violinist, Mozart duet. Szilard on the phone, I found the neutrons. Then it was clear it could be done, somehow. Nobody paid attention. Fermi went to the Navy, they listened politely and threw him out. And Fermi was not going to go around and sell his goods to other people. Now, Szilard was a very ingenious person. He could do everything, with one exception. He could not drive a car. And therefore, in a nice day in the summer, when I was guest lecturing at Columbia, he came to me, "Will you drive me out to Einstein?" I did. We arrived, not without difficulty, because Szilard did not know the address. We asked everybody, including a very nice 80-year-old girl approximately, long hair. Einstein. Never heard of him. You know that nice old man with the white hair? Oh, yes, over there. So we found Einstein. And Einstein was democratic and invited the chauffeur to have tea together with Szilard. So I was there when Szilard took the letter out of his pocket. Einstein read it with great interest. He obviously read it for the first time. He did not write the letter. The letter was written by Szilard. And the letter was addressed to Roosevelt, because I told you Szilard knew everything. He also knew how to get Roosevelt's attention. That was not by talking to him. That is by getting Einstein to sign a letter to him that Roosevelt would read. The letter was signed on the 2nd of August, 1949. 4 weeks later, Hitler attacked Poland. The letter did not get to Roosevelt. Szilard gave the letter to a friend of his who knew Roosevelt, and he waited until he could see the president. And he did see the president in October, when Poland was defeated. It was defeated by the alliance of the great forward-looking people, Hitler and Stalin. At that time, Roosevelt fully realized, much more fully than most Americans at the time, that there was very big trouble ahead. And that was the time when Szilard's friend showed the letter to Roosevelt. And Roosevelt went into action right away, asked the head of the Bureau of Standards to call a meeting, to which everybody, even I, was invited, about 24 people, to give advice how to go about it. One of the people invited was Fermi. But Fermi said he's sick and tired of the whole thing. He does not want to hear about it. I was Fermi's good friend, so I had the next mission. I was promoted from chauffeur to messenger boy. Went to Fermi, come to our meeting. No, I won't. But I tell you what I would say if I came. So he did not come. And when my turn arrived, I said, here is what Fermi would tell you if he were here. The way to make things work is not to use uranium, not to use it directly. But uranium has two isotopes, meaning two nuclei, two kinds of nuclei, having the same charge, the same chemical behavior, the same number of protons. But the number of neutrons is different. The neutron-rich isotope, uranium-238, is very generally available and undergoes fission only if bombarded with fast neutrons. Does not react with slow neutrons. The other isotope, U-235, present only 0.7%. But that works with any kind of neutron. So what is to be done is to make a reactor. Where neutrons get slowed down and then allowed to interact with uranium. And at low energies, this little uranium-235 becomes very effective and keeps the reaction going. And while the reaction is going, new elements are formed, in particular plutonium, and that can be used for nuclear explosive. All of this I recited, not because I knew it, but because I knew Fermi. And the armed forces were represented by a colonel who said it cannot be done. And a long discussion. Finally, I had my chance to contribute to it. And again, not my wisdom, but that of Fermi. I said, we want to work on it. We have university jobs. We don't need support. Uranium is dirt cheap, no trouble. But to slow down neutrons, you have to have very pure graphite. Collisions, elastic collisions, by giving recoil to carbon nuclei, reduce the energy. But the neutron must not be lost. It must undergo 100 collisions and more without getting absorbed. And graphite will not do it unless it is very pure. And therefore we need pure graphite. And therefore pure graphite is expensive and we don't have the money. And we want to get going. And how much do you need? $20,000. All right, says the colonel. $20,000 you can get. The day was saved. And Szilard nearly murdered me for not having asked for more money. Of course, I was innocent because I was merely quoting Fermi. That is how we got started. I got involved. I had one great virtue. In one respect, I was better than anybody else. The two main characters, Fermi and Szilard, did not like each other. And I was on good terms with both. I was needed because that way Fermi and Szilard could be gotten together. So I was invited into a project from the very beginning. And during the beginning of the war. It was not yet official, but almost official. One day, walking back from lunch, again with my good friend Fermi, you know, Fermi speaking, you have worked on the energy on the stars. They are not made by uranium. They are made by a collision between hydrogen nuclei. Very clumsy process. If you use not hydrogen, but heavy hydrogen, not two protons, but two hydrogen-like nuclei, each having a proton and a neutron, then you could release energy. What about it? Hydrogen bomb. Heat it with a fission bomb and get the thermonuclear reaction. The reaction depending on the energy produced in a reaction to produce more energy, heat up more material, propagate. I thought about it carefully and found out it could not be done. And in a few days, I got on a long walk with Fermi, and I proved to him it cannot be done. Why not? Now, you know, all kinds of things about that are secret. But why it could not be done is not secret. And that I can tell you. At the relevant high temperatures, practically all the energy goes uselessly into radiation. And very little energy into the motion of particles that were to collide. And even a fission bomb would not give enough energy to supply the radiation at these high temperatures. Fermi was completely convinced. A few months later, Pearl Harbor, I was invited to participate full-time. Fermi and some others were already working very effectively on the reactor that was to produce the explosives for the atomic bomb. I was invited but left without a job. Do whatever you like. I was also given a nice collaborator, originally from Poland, Emil Konopinski. I told Konopinski, all right, I have this nice idea from Fermi that doesn't work, the hydrogen bomb. Let's write it down and prove that it doesn't work. So no other people will uselessly spend their energy on it. The more we worked on it, the less complete our proof got. We found a way out. If the energy released in a reaction was very fast utilized for further collisions, there may not be time enough to emit radiation. You don't work with the stuff in equilibrium. You try to emphasize the fast-going reactions. And that looked good to us. Within a short time, Oppenheimer got the charge of taking care of the theories of nuclear explosions. He called a conference to which I was invited, and Konopinski. We presented the idea, and it seemed so attractive that practically the whole conference was on it. And furthermore, Oppenheimer reported back to the leader of the whole project, Compton, telling him, you know, there is much more in this than just fission. This is much too complicated a matter. We cannot just do it in the existing institutions. We need an extra secret place where to do it. He recommended Los Alamos, and that is how Los Alamos got started. In less than a week, I'm sorry, less than a year, we assembled at Los Alamos. At first, a couple of hundred people. At the end, by war's end, the workers were a few thousand. But not on the hydrogen bomb. Why not? The reason was that the fission bomb turned out much more difficult than we imagined. In the fission bomb, straightforward, if you put together enough material, so before the neutrons could escape, they made a fission. Then the fissions multiply, and you got a big yield. But you had to put the parts together. And the moment there is a neutron there, the neutrons will multiply very fast, and before enough material gets assembled, you get an explosion, but not a very big one. Still, with good designs of guns, we could do it, but then came the real great trouble. In order to make a fission bomb, you needed a material that could make this fission. And we had two materials competing for it. The rare isotope of uranium, of which we could make little, and it worked, and the new material that you could make in the reactor, plutonium, that also was very good in fissioning, but it turned out that sitting all by itself, it started a few of them to do fission and emit neutrons. The material for the fission bombs, of which we had a lot, that material, plutonium, had so many neutrons that it was practically certain it would pre-detonate. That is, start reacting too fast and disintegrating in the end without a big yield. Now, at that time, at that point, one of my other Hungarian friends happened to visit Los Alamos. He was not a physicist. He was a very remarkable mathematician, John von Neumann. The most important, practically important thing that he did was to, in the field of computers, where he introduced the idea of self-programming, of programs that depended on what you have already found, of computers that almost acted as though they would be thinking. But he was just beginning in that. And he was a very generally interested man and was willing to puzzle about anything. He visited us in Los Alamos, and first evening I invited him, told him about our problems. I remember the evening very clearly. We had little houses there which had badly needed heating at that high altitude, but the heating did not work very well. So it worked, but it gave little explosions, made us jump. And my friend Johnny von Neumann's remark was, I will never live it down if I get killed in Los Alamos by a low-grade explosion. Well, then and there, I explained to him one of the ideas that a colleague, Seth Neddermeyer, had in order quickly to assemble. You don't shoot two parts together, you take a shell, surround it by high explosive, and then bring it together from all sides. Very obviously called not explosion, but implosion. Not a new idea at that time, and not a highly favored one. But Johnny made quick calculations how it would work and found, yes, uranium metal or plutonium metal is of course incompressible. Then when you try to assemble it, it had to accelerate faster and faster on smaller and smaller radii. And he calculated the pressure to be 100 million atmospheres at the concentrated innermost point. At which point I said, whoa, I know enough physics that at these high pressures, uranium or plutonium is no longer incompressible. And that was a great thing, because if it's compressed, then less of it is sufficient in order to make an atomic bomb. And we were racing time to make enough plutonium. There was too little of it. The implosion not only made better bombs, but it made more of them at an earlier time. And I must say, we had a remarkable experience. Next morning to go to Oppenheimer, who at once saw the point, and the full force of the laboratory, Los Alamos, was directed toward that implosion. All the details are classified, fortunately, because if that would not be the case, I would talk too long. We had the bomb. I was told that I must tell you what I thought when the first bomb exploded, and that I will tell you. A small number of us were to observe it from a distance of a little more than 10 miles. We were told not to look at it, but I looked at it. We were given welding glasses, and because I had estimates that even resulted in higher yields, I put on an extra pair of dark glasses and the welding glasses and gloves so no light would come in from the side, and I was looking straight at it. And at the proper time, I saw a weak light. It was 6 o'clock in the morning, practically dark. A weak light on the horizon that started to spread. In the first 2 seconds, my clearly remembered impression was, is that all? And then I remembered I had all these absorbing substances there. So I tipped the absorbing glasses and looked out at the sand next to me. I told you, early morning, still practically dark. 2 seconds after the explosion, bright daylight coming in. Then I was impressed. And of course I knew that soon this would be used for a very real purpose. Now let me change the subject to something in which I then had no part and should not have had a part. But there was a lot of discussion about it. How do we use the atomic bomb? The war against Japan was practically won. Did we need it? There is a lot written about it now, and there is a widespread opinion that we really need not have used it, should not have used it, that we did use it only because we were afraid the Soviet Union would come in and demand much too great a part of the booty. I think that that argument is wrong. I now know that we could have won the war, not by use, but by demonstration. At least I think that's probable. And in a way, I would have liked it better that way. But to say it was wrong to use the bomb, let me argue the other side of it. The Second World War killed approximately 50 million people. The atomic bomb that ended the war killed a little more than 100,000. That number of people would have been killed, and more, quite a bit more, had the war lasted a month longer. Furthermore, the Soviets did come in before we used the bomb, or about the same time. And they caused the division of Korea. That in turn led to another war and led to the establishment of a horrible and inefficient and starving government of North Korea. Without the Russians, the peace could have been made very much better. I am not telling you that Hiroshima was fully justified. I am telling you with a lot of emphasis that the argument has at least two sides. Now let me come to hydrogen bomb. Originally, Los Alamos was to pursue the idea of the hydrogen bomb. We were much too busy really to make the fission bomb work. But it was understood that as soon as we succeeded, we would go ahead with the hydrogen bomb. On the day Japan surrendered, the 15th of August, 1949, Oppenheimer came to my office and said, the war is over, no more work, not on the hydrogen bomb, not on anything else. This was a decision that stuck, that I knew would stick. I knew it was hopeless to fight it. I did not like it, but I went back and did pure physics. In the course of time, I felt I should go back and help along in Los Alamos to some extent, which I started to do. And at that time, the Soviets, much sooner than most people on our side expected, detonated an atomic bomb. That was 1949. At that time, I felt that they will get ahead of us in the hydrogen bomb as well, unless we act. And furthermore, it was wrong to stop with partial knowledge. We should work on the hydrogen bomb. We should find out everything about it that we possibly can. The majority of the physicists were against it. They did not want to work for any weapon unless a war so obviously important as the war was with Hitler was going on. I want to tell you, I worked on the hydrogen bomb. I made some contributions. If I had not done it, others would have done it. No importance. But one thing was important. The hydrogen bomb was top secret. The number of people who knew about our discussions on it were very few. And the number of people whose advice was taken in Washington was also very few. Among those people who had a possibility to be listened to, there was perhaps not more than a dozen, all good scientists. I was the only one who said it could be done and it should be done. The senator who made the relevant decisions Senator McMahon, asked me to come in and brief him. Before I could do that, a representative of the Scientific Advisory Committee, called GAC, General Advisory Committee, the secretary came to me and said, please don't go to see the senator. Don't spoil the opinion, the unanimous opinion, that a hydrogen bomb cannot be done. It was not an easy decision. And it made my work in physics almost impossible later, because all the good collaboration possibilities were gone. I went and saw McMahon. I did not see Truman. I saw him and one other important person. Truman heard about it and made the decision. Go ahead and do anything you can on the atomic bomb or the hydrogen bomb. Now, the way how that discussion went among scientists is an important historical fact. And I don't want to spend the time that I have already used up. I don't want to tell you more about it, except I want to tell you where you can find out about it. And I would like to recommend that the university here do a little bit of multiplying an important document, which is the April 1st issue of the Bulletin of Atomic Scientists. That was the opinion of the scientists, with a big article of Einstein equating the hydrogen bomb to military dictatorship. I also wrote in it a rather ineffective one, Oppenheimer a short one, Urey a thoughtful one. I think it is a very interesting document. And it shows with how many doubts we started on the job. What did the Russians do? We did not know. We know today. On the atomic bomb, they started out without our ideas. But they had in Los Alamos an exceedingly intelligent spy who was my good friend. Of course, I did not know he was a spy. Klaus Fuchs. He gave a complete design to the Soviets, and the Soviet atomic bomb of 1949 was a very good copy of what we did. But our ideas about the hydrogen bomb were then just developing. That was not transmitted to the Soviet Union. In the end, after a lot of discussion, I had a solution convincing enough so that none of my colleagues and opponents who did not want it to work could say, we don't believe it will work. It was decided to go ahead. It worked in the early 50s, and I in turn went ahead and used this occasion to start a second laboratory in California. I felt that such a second laboratory is needed because in important matters which are not open to general public debate, but is decided by a few people who are cleared, who have access to secrets, at least two independent groups should address every problem. And so I advocated a second laboratory in Livermore. Now, about the complicated advocacy of that, I want to tell you only one amusing little support I got, and very big support. The man in charge in California was a well-known man responsible for the cyclotron, Ernest Lawrence. And I was advocating a second laboratory, advocating a hydrogen bomb. And Lawrence was asked, now, Stella, can we believe what he says? Isn't he exaggerating? And Lawrence, who wanted to help me, gave a wonderful answer, really inspiring. He did not say, yes, trust that Stella. He said, I don't know. I sometimes agree with you, sometimes I don't. If Teller says something cannot be done, he's frequently wrong. But if he says something can be done, he's always right. Now that was a much more strong support than I could have gotten by saying I was right. Much more persuasive. And we got the second laboratory. I would like to conclude by jumping to the present day and to the future. The Soviet Union is no more. Why? Because the United States, in the war in the Gulf in 1990-1991, showed that we had the best weapons and could use them. Showed that we could defeat an army 1 million men strong with practically no losses. The Soviet leadership knew all along that we were technically ahead of them. But they thought we were appease us. We never can make up our minds. The United States won't count. In the Gulf War, we showed that we can make up our minds. And the Soviet government collapsed 4 months later. That was roughly 4 or 5 years ago. In the meantime, what do we do? The proliferation of atomic weapons is a worry on everyone's mind. I claim that the popular opinion, there is danger in knowing too much, that popular opinion is wrong. I think the real danger is not to know enough. 1945-49, people said, we had the fission bomb, there won't be anything more. It turned out that the hydrogen bomb came easily. The people who are now arguing for no proliferation say stop, everything else will stop. What I'm going to tell you, I believe, with a clear and strong negative sign. I believe the opposite of it. But this is the today popular opinion. Wars are caused by weapons. The best weapons are made by the United States. Therefore, if only the United States will stop making weapons, there will be no more wars. I think wars are stopped by strength and weapons in the hands of those who want peace. That is how we have used the atomic bomb in peacetime, balancing what the Soviets could do, but never actually using them. Today, people are afraid of science, of too much knowledge. I think we must be afraid of nothing but too little knowledge. I have with me a cartoon. I really should have made arrangements to project it. Two old men discussing, one having written a long, illegible equation on the blackboard, ending in an equality sign. And the text is, my feeling of responsibility to the community convinces me that I should stop here. This is something new in the United States. The United States had been unequivocally for progress. When I arrived here 60 years ago, whatever was new was good, even if it wasn't. It may have turned out not to be good, but we took it for good in the first approximation. And that led to enormous strength. Today, everything that is new is under suspicion. How to change this? I don't know, but I will tell you. We not only should pursue what is new, we should turn it to the advantage, not of ourselves, but of everybody. I wish I could give you good examples. I will give you some, not because I think the best, but because the only ones I can think of better ones. Develop a missile defense. Missiles today are more dangerous than atomic weapons. They are widely available and can take war in a very short time for that are not announced in advance for a good purpose. One thing we could do in everybody's interest, not in ours. Second, much better weather observation. Today we have weather observation over 10% of the world. We could have it over 100%, including oceans, from space, including the measurement of wind velocities at all altitudes, which make it very much easier to find out not where weather is, but where weather will go. The practical application of the great and developing science of biochemistry, which is making great progress, but the progress is not applied in agriculture, in practical purposes, because people are much too afraid of what is new. Again, this could be of advantage to everybody. And last but not least, and that is where I want to close my talk, you all have heard of the possibility of a collision with a meteorite. The last biggish collision was with my meteorite that arrived 5 months after I was born in Siberia, was a little more than 100 feet across, exploded in the air, and laid flat a few thousand square miles of forest. Had that happened over New York? No New York. That kind of collision is expected, maybe once every few hundred years. The one really big explosion was a collision with a meteorite more than 10 miles across. And we have very precise knowledge of it. A big crater in the Caribbean. The date, 65 million years ago. It killed 90% of all living beings. It ended 70% of all genera, including it put an end to the dinosaurs. Our ancestors, being small and modest, not needing terribly much sunlight, which was excluded by the dust raised by this horrible process. Our ancestors had their chance then. I want to be unfair. I don't want to be succeeded by something even better than we, and I would prefer not to go the way of the dinosaurs. Now, this is something that we know how to do, and the first steps are being taken now by a better observation of all meteorites that might collide with us. We have methods, actually more gentle methods than atomic explosions, to deflect meteorites, except the very biggest ones. For the very biggest ones, I'm afraid, the only way to handle them are with nuclear explosives. All these are possibilities to be undertaken jointly for joint purposes. I think science will not again become popular unless and until we clearly find ways how to collaborate with others, how to overcome secrecy, how to develop what is new and promising, not for one military purpose, but for all purposes, including the military purpose of preventing wars. Thank you very much. Short questions.
We have time for a couple of brief questions. If anyone has a question, to come to the microphone.
If you have no questions, you either have understood everything or nothing. Question?
Yes, I had a question. You discussed, of course, that a strong peacetime deterrent is important to preventing war from occurring. What about the possibility of a suitcase bomb, for example, by a state that we can't identify? Suppose somebody was to blow up a major U.S. city or another major world city, and we don't know who did it. How do we respond to that? Do you have any thoughts?
I did not hear the question sufficiently. Could you repeat it?
Sure.
No, you repeat it.
I can come up there and just talk loud.
Suitcase bomb that we don't know who caused it. How do we retaliate?
Look, there is an incredible amount of damage that you can put into a suitcase. Not only a bomb, biological agents. The defense against a suitcase bomb exists. And the best defense, the only defense, is infiltration. These things cannot be done by single people. You need at least a somewhat sizable organization. by participating, by telephone tapping, and a number of other things. You can do something about it. And if there is international cooperation between scientists trying to prevent, not only here but everywhere else, terrorism, I think we'll make a good record. I would like to tell you that as far as I know, terrorism was something very important and very disastrous around 1900. Terrorism was the immediate cause of the First World War, when the Crown Prince of Austro-Hungary was killed in Sarajevo. At that time, the terrorists were aiming at queens and prime ministers and whatnot. Today we have democracy, and the terrorists are aiming at all of us. In the meantime, there seems to have been much less terrorism. Now it's beginning to develop again. It's an important problem, but it has solutions which are not the same as the others.
Given the recent shutdown of the reprocessing plants at Hanford and Savannah River, and the slow shutdown of the gaseous diffusion plants, and the recent non-proliferation treaty that's currently being signed and ratified, what do you think is the future of U.S. weapons development and deployment?
Because of nuclear waste, what do you think of future nuclear development?
Come to my lecture. Tomorrow morning, 10 o'clock.
10 o'clock in the law building.
Actually, the proposal is make reactors foolproof by the only possible way: exclude the fools. Everybody, including you and I, are foolish. And we can be foolish in a very ingenious way. All nuclear accidents have been due to foolish, easily avoidable mistakes. The way to avoid mistakes altogether is to put reactors underground and make them completely automatic.
In your presentation, you spoke highly of J. Robert Oppenheimer. I wonder if you'd be good enough to tell this audience the role that you played in the destruction of his career. Do you want to tell him?
That's all right. Next.
May I have the question?
The role you played in the Oppenheimer.
Listen. A long story, and I will give you an answer. I intended to testify for Oppenheimer. I couldn't, because I was shown Oppenheimer's own testimony, where he, under oath, says that he has accused a colleague and friend, Håkon Chevalier. And under oath he said he has wrongly accused him of leaking information to Russians. Then, under oath asked, why did he do it? Did you do it? Oppenheimer's complete answer, and it's published now, you can look it up, because I was a fool. Chevalier has written a book about it. The title of the book is Oppenheimer, The Story of a Friendship. It is a very, very sad affair, and very terrible for myself. I would rather not talk about it, but the main reason is that Oppenheimer, for reasons not explained by him, not explained by anybody, has behaved in a manner that made it a little difficult to have the feeling he can be trusted.
I
wanted to ask a little broader question, and that was that there was a book that just came out called The End of Science. And I wonder what you, as a distinguished scientist, has to say about this theory that science is essentially over.
I did not see the book End of Science. I have to acknowledge, we are now spending maybe 100 times more on science than we did when I was young. For that enormous input, we get altogether a lesser response, lesser effect than we had 100 years ago. Complicated reasons. But I think the present trend not to trust in innovation is the most menacing for science. We must reacquire the taste for what is new, what we should try.
I was talking to you earlier today about the polarity of the Earth, and you said that maybe it was due to the meteorites. And I had read someplace, I remembered this, that it didn't affect the plant or animal life at all during the time periods, and when the polarity switched. And so I was wondering if you thought it plausible that the polarity switch might be caused by solar flares, say, instead of meteorite collisions.
The Earth polarity switch caused by meteorite.
Thank you for the question. Will that be the last?
Yes, that's the last.
Let's make it the last. I will give you a long answer because it's a very interesting subject. The Earth is a magnetic dipole. The poles of the magnet almost coincide with the poles of rotation. But we have conclusive evidence that the poles switch. Sometimes the magnetic pole is like this, and sometimes like that. The switches occur approximately 2 or 3 times in a million years. Why? I don't know, but I have an explanation. The generally accepted explanation for the magnetism of the Earth is that the Earth has a liquid iron core which is turned around by gravitational release of energy. This will give all kinds of magnetic fields coupled in complicated ways, but in this coupling, order is made by the rotation of the Earth. But there are 2 good orders, all poles pointing this way or all that way. Now, the impact of maybe a mile across meteorite ionizes big amounts of the atmosphere and moves it, and moves magnetic fields in the surrounding of the Earth in a very effective way, and that represents a few percent of all the magnetic energy that could upset the somewhat weak equilibrium that ordered the magnetic moments. The Earth may lose its ordered magnetic field, and then the rotation will realign it in equal probability up or down. The wonderful possibility of science is to have the opportunity of making wild guesses. The guess I gave you is wild. I'm looking and looking for ways how I can make it true or untrue, prove it or disprove it. I worked a lot on applications. If I would have done all the time what I like to do, I would have not looked at anything but science. By too much application, too much, and even more by too much fear. There may be an end of science. That would be a very dreadful thing. And I think the possibility of the end of science is the greatest danger we are facing at the present time. Thank you very much. Thank you again.